All right. Okay, we'll get started now. Sorry about that. All right, so we're just going to jump right back into it. So right now we are in Chapter 5, Thermochemistry, where we are talking about energy involved in chemical reactions. So we talked about energy in Chapter 1 previously, but just generically talking about kinetic versus potential energy and how chemists think about kinetic versus potential energy. So kinetic energy we know to be 1/2 mv squared. That's for like a single object moving in space with some mass, some velocity. But for us chemists, what we tend to care about more is just temperature of a sample, which tells us the relative average kinetic energy of that sample. So hotter samples just have overall more kinetic energy. Potential energy, on the other hand, is a topic that definitely differs from our physicist neighbors, where we still think about particle positioning from one another, but mainly for chemists we care about attractions and repulsions of charges, where typically attractions have a negative potential energy and repulsions have a positive potential energy associated with them, and the equation for Coulombic attraction. So we talked about that previously. So the new terms for this chapter is we're going to look more closely into heat and work and how those relate to us calculating total internal energy for a compound, and so, or for a system. And so we have a definition for internal energy of our system is the sum of all of the kinetic and potential energy of our system. All right, so we did a demo, our favorite demo earlier this week, showcasing, and what I wanted to highlight there is in this chapter, we cannot be selfish. We got to think, how is the reaction changing? All right, just because we feel something get hot, we feel it get hot. For some reason, we associate that with like a positive sign because we get warmer. But no, we get warmer because we are the surroundings. The reaction is losing that energy. So there's a negative sign associated with that. So we tested our skills here in thinking, okay, how does the system change in these different phase changes to turn a solid into a liquid? We have to heat it up. So the sample increases its energy to make those phase changes. Same thing for liquid to gas. We increase that energy of the system to make it heat up. And so therefore the opposite, turning a gas into a liquid, we would see a decrease in energy there because of opposites there, opposite phase change there. So let's look at another example here. This time thinking about kinetic and potential energy. So kinetic energy, remember, we associate this with temperature, right? For us chemists, we care about temperature. And potential energy, we care about like, particle position, right? So let's think about, what's happening when a pot of water boils, right? You put a pot of water on the stovetop, you crank it up until that water starts to boil. So at that point, when that water is boiling, you actually have two different phases present. You have liquid water still in the pot that's actively boiling, but you also have water vapor, the steam above it. All right, so let's think about that. We have water boiling. It's at 100 degrees Celsius, right, liquid water. And then we also have that steam there that's also at 100 degrees Celsius. So let's compare those two things. We're talking about the water in the pot and also the steam around it. So let's compare the kinetic energy of those two things, the water and the steam. Look at all the information I gave you here. How are their kinetic energies related? Are they the same or are they different? Remember how chemists define kinetic energy. We care about what? The temperature. So what's special about the water here and the steam? They're both at the same temperature, so how are their kinetic energies related? They're actually the same. Yes, their kinetic energies are the same here. All right? Because of the temperatures are the same. All right. But what about their potential energy? Potential energy cares about what? Particle position, right? Are their potential energies the same? No, they're not the same. They're different because liquid water has all the particles like all mashed up together, all right? So their distance from one another is really close, while, the distance between particles in the gas phase is quite far away. So their potential energies are different. All right, so we'll go into more detail about those things. When we add heat, we have to continually heat water to get it boiling. And what we're doing is actually changing the potential energy of the sample. The sample actually stays 100 degrees Celsius all the time when we boil water. It stays at 100 degrees Celsius. That added heat that we put to a pot of water to keep it boiling actually goes to breaking those potential energy attractions between particles. All right, so that's how energy is important in physical changes. All right, okay, so to again compare these types of energy, the physics definitions versus the chem definitions, again, keep in mind kinetic energy related to temperature of our sample. It's potential energy, that's the new one here that oftentimes confuses students. So we, this is like a classical physics diagram of the transfer of kinetic and potential energy in some type of process like this, where our snowboarder goes up and down the hill. And so during this process, when the snowboarder is up here on this, at the top of the hill, we see that the potential energy is highest. But when he starts moving down and potential energy is converted to kinetic, he gains the most kinetic energy at the bottom and has zero potential energy. And so we see these bars on the sides here, they'll go up and down because we're transferring kinetic and potential energy. But what's interesting here is that total energy stays the same the whole time. Right? All we're doing is transferring the kinetic to potential energy over and over and over again, as long as this is like a perfect like physics system, right? So to further think about potential energy, in this diagram, the snowboarder's potential energy is the lowest when they're at the bottom of the hill. That's where all of that potential energy has been converted into kinetic energy. But for chemists, potential energy is a little bit different, all right? That for chemists, we actually want negative potential energies. So like for physics, we stop thinking about potential energy once it's zero. Once your object has hit the floor and there's no more kinetic potential energy, then we're done. But for chemists, we actually want negative potential energies, and that's actually a good thing, right? So in chemistry, and this you should, these are one of the mantras you should say to yourself over and over and over, all right, this weekend, is that in chemistry, potential energy is actually the lowest when particles of matter are attracted to one another and close together. And this usually results in negative values, and that's good. Right? And so this is definitely different from our physics definitions, all right? So in chemistry, a potential energy of zero actually means that your particles are neither attracted or repelled from one another. They're actually not interacting at all. All right, so we actually don't want a zero potential energy. We want to talk about attractions and repulsions. So what we want to look for are negative potential energies of attracted particles, and they're close together. And so here's another way to think about it. We already looked at this diagram where we looked at Coulombic attractions. Again, in chemistry, potential energy is lowest when particles are close together and they're attracted. So we looked at this diagram that said, okay, when attractions are really strong, so this was attractions, when like a positive and a negative particle were close together, we have really, really strong attraction. So this is a negative potential energy. Versus if we have two like charges, like two positive protons or something, or two negative electrons, when you bring them close together, they start to repel one another, and that's a positive potential energy, and that's not super favorable to us, right? So again, we want to be operating in this attractions realm where things are attracted and close to one another. We get this negative potential energy that is very, very stable, and so therefore most commonly seen in nature. And so we can relate this to chemical bonds, all right? So this graph over here is actually the same thing as the bottom graph of our Coulombic attractions. This graph is saying, okay, when bonds are broken, potential energy of that system actually approaches zero. When you break bonds, you're separating those atoms so far away from one another, they're no longer interacting with one another. But when you form a bond, all right, over here. So we're like forming bonds over here, form bond. To form a bond, you bring atoms close together. And if those atoms are close together and they're attracted to one another, then we get this stable negative potential energy that keeps those bonds formed, all right? Okay, so thinking about, we're just looking at this attractions hill, all right? We have forming a bond is a negative potential energy. When we break those bonds, separate them, it approaches zero. If you think about this hill and how energy is involved to go up this hill, all right, in order to go from a bond to breaking a bond, we have to add energy to the system to do that, all right? You need to add energy to the system to break a bond. Energy is required to break a bond. We're going up this hill. Versus if we want to form a chemical bond, we go down this hill, all right? If you had like a ball rolling here, would that ball roll down this hill automatically to form a bond? Yes, it would, because substances are always trying to find this energy minimum, and that's what these negative potential energies allow us to do. We're trying to find these energy minimums. So the big idea from this graph is just taking what we already knew from Coulombic attractions, just thinking about attractions, is that breaking a chemical bond will always require energy, always. Forming a bond is the opposite, and it actually always releases energy. So breaking a bond, you go up the hill. Forming a bond, you go down the hill. And so energy is involved in each of those processes. So if we go down the hill, we form a bond, all right? But if we go up the hill, we break that bond, right? So always, breaking bonds are always endothermic processes. Forming a bond is actually an exothermic process because it releases energy. And I'll define those terms in a little bit, all right? So keep that in your mind, always. Because this is where I have a tiff with biologists, and I'll talk about that later. Okay, all right. Okay, so let's check our understanding for some of these conceptual things. Kinetic and potential energy again. So how do we compare kinetic energy of samples? What do we look at? Kinetic energy. Temperature, yes. And then potential energy, we learned that potential energy is lowest. All right, so potential energy is lowest when our particles are what? Attracted and close together. Yes, close together. Okay, so let's look at these two pictures. So we have oxygen, it's a solid at 31 Kelvin, and then we have oxygen, it's a gas at 194 Kelvin. So comparing these two pictures, which one has the greater kinetic energy? Which, B? Yes, B. Why? What did you look at? You looked at the temperature. That's all you looked at. That, 194 Kelvin is greater than 31. Yes. So we're just looking at temperature when looking at kinetic energy of these samples. All right. What about potential energy? Which one has the greater potential energy? So remember our definition here. Potential energy is lowest. It's most negative when particles are attracted and close together. So which one has the greater potential energy? B, yes, because the particles are far apart. Yeah, far apart. So far apart. So that means that the oxygen solid here, those particles are close together. Okay, so it's going to have a negative potential energy. If we think about the hill thing, or our hill, right? Solid is over here because your particles are close together, and then gas would be over here because the particles are further apart. All right, so the gas sample has the higher potential energy. It's still going to be negative, it's just less negative. Okay, so based upon our answers there, which substance, A or B, has the greater internal energy then? If internal energy is the sum of all kinetic and potential energy, and we just figured out what those are, B has to have the greater internal energy, yes. Okay, so that was like a lot of work to just figure out that substance B has more internal energy. So here's the thing. We actually will really never calculate internal energy for a sample. We will never look at a sample of water and be like, bam, that's the value of internal energy for that object. No, what we care about as chemists is actually the change in internal energy for a process. We want to know how much energy is like required to make this change, to go from picture A to picture B. That's what we don't care about the absolute values of internal energy. We care about how is internal energy changing for a process. All right. So if we think about it, you know, we already deduced that the solid has a lower internal energy, the gas has a higher internal energy. So what we chemists care about is what is the energy difference between those two states? What is the difference in energy to turn that solid into a gas, right? That's what we care about. We can measure delta E. We can measure change in energy for a process. We can't measure the actual energy for these two states, all right? So for now on, we are going to be measuring energy changes for a process, not like absolute energy for looking at an object, all right? Okay, there we go. All right, so how do we measure change in internal energy? There's two ways to do it. We can either do final minus initial, okay? But I told you, right, like we don't actually ever measure the absolute internal energy for like state 1 and state 2. That's really difficult. So what we do instead is recognize, oh, the change in internal energy is equal to the sum of all the heat involved in a reaction and any work that is done in a reaction. We can measure these. Okay, we can measure these. We can measure heat and work. All right, so the heat and work involved in a chemical process is related to the change in internal energy for that chemical process. Okay, so we will care more about heat and work here. All right, so let's define these. Q is heat, okay? And so some definitions here for the signage, because I told you guys, right, if you're gonna mess up in this chapter, it's gonna be due to sign. All right, so if Q for your system, so if your system is changing its heat and it's a positive value, we call that an endothermic process. That system, your object that you are looking at is gaining heat. It's gaining heat, all right, in some way. When Q is negative, that means your object is giving off heat, all right, and that's an exothermic process. So when we think about it, if we have an exothermic process, our object is giving off heat, what do we feel? We feel it get hotter, right? We feel it get warmer, right? Because we are the surroundings, the object is the system. But then endothermic processes seem a little bit weird. If you're holding an object and its Q is positive, it's absorbing heat. Where is that heat coming from? You, the surrounding. So what does it feel like when that object has a positive Q? It feels like it gets cold, which is weird. It gets cold, but Q is positive. Doesn't that sound kind of weird? But again, it's because the object is gaining heat and it's stealing it from you, which you are the surroundings. Okay, so that's Q, heat, exo versus endothermic, right? I always like to remember exothermic means like big explosion, lots of heat given off, and that's a negative value. That's how I memorize it. Okay, so work on the other hand, you know, physicists, they define it as like work equals force times a distance. As chemists, we talk about work in terms of expansion, gas expansion and compression. So here's a nifty equation to help you just determine the sign of work for a chemical process. So if you think of like pistons in your car, that is work because your pistons are changing its volume. So work of your system is equal to negative, usually against a constant pressure like the atmosphere, times change in volume of your system, all right? So this is called pressure volume work. So let me give you an example. When work of your system is positive, what that means is your system is gaining work. Work is being done on your system, just like Q, right? When Q is positive, you are adding heat to your system, to your object, so it felt like it was getting cold. So if I have like a balloon and I do work on it, I'm squeezing it really, really tightly, so how is its volume changing? It's decreasing, yeah. So what we see here is that work is done on your system, volume decreases. So if volume decreases, delta V has what sign? If you're decreasing your volume, it's negative, yeah. So just plug that into this equation. A negative delta V times a negative sign gives you a positive value of work. All right, so a positive work on your system means a decrease in volume. All right, versus a negative value of work for your system means that your system does work on the surroundings, okay? That it's giving off work, I guess. See, this it's hard to define, right? So your system is doing work on the surroundings. So what it's doing, if I'm your object, all right, I'm expanding against the surroundings, so my volume is actually increasing. So, but if you like equations, which I do, I like equations, your volume increases, so delta V in this case is what sign? Positive, so plug that into this equation. When your volume of your system increases, positive times a negative, it's a negative value of work of your system. All right, okay. All right, so let's put those things all together. Oh, nope, not yet, not yet. Okay, so again, we need to be very, very careful with defining system and surrounding. System, for the most part, is the chemical reaction we're looking at. And then we have to be careful about the surroundings. Usually you are the surroundings. If you see a temperature increase, that means that your system released energy, it's a negative Q, right? Or if you see the temperature go down, it means your reaction absorbed energy, and that's endothermic. So you are typically part of the surroundings. The reactions that we are going to be usually measuring are closed systems, meaning that matter is confined in a spot. That matter is not exchanging with your surroundings, but typically energy can be transferred between system and surroundings. And remember, you are the surroundings. This is you. So we can measure changes in like temperature of our surroundings and then relate it to our system. Right? Because the first law of thermodynamics says that energy cannot be created nor destroyed. So if we define our system and our surroundings carefully, and we know that the energy of the universe never changes, we can say that energy involved in your system is going to be transferred into your surroundings, and we can measure the surroundings. All right, so yeah, so we're going to be constantly using this idea that energy changes in your system is whatever is lost in your system is gained by your surroundings. So instead of writing it this way, sometimes I'll write it this way, like whatever energy is lost, the negative of whatever is lost is always whatever is gained somewhere else. All right. Like energy lost somewhere is gained somewhere else, and we can measure that one, or the other way around. But the important thing is this negative sign. Do not forget that negative sign. We need it. If you are doing calculations and you get a number like you can't solve it, it's probably because you forgot a negative sign. Okay, so there we go. All right, so let's put it all together and make sure we get these signs right. Put yourself in the situation of your system. Okay, remember, change in internal energy equals heat plus work for your system. So let's say we have a reaction and it absorbs that much heat and does 10 kilojoules of work on the surroundings. What is delta E, or change in internal energy? So remember, it's Q plus W, but it's of the system. So I give you numbers, so 25 and 10, so you might just think, oh, it's 35. 25 plus 10. But we have to be very careful with how things are worded, because it's not necessarily 25, positive 25. It might be negative 25 depending on how it's worded. So let's go through this. So 25 kilojoules of heat, that's Q of my system. But is it 25? So the chemical reaction absorbs 25 kilojoules of heat. So what is the value of Q system? It is positive 25. Okay, great. All right. So then this other number, this seems to be like work of our system. And so I say it does 10 kilojoules of work on the surroundings. So what is work? Is it 10 or is it negative 10? It is negative 10, yes, because it is putting work out there. It's putting work out there. All right, so it's negative 10. So now these are the two numbers we add together. So 25 minus 10. The answer is 15 kilojoules of internal energy change here. All right? Yes, we can't. But you know 50% of students, they'll just do 25 plus 10 and call it a day. All right, but we got to do reading comprehension. Yes. Okay, so let's look at this other one. Consider an exothermic combustion reaction that occurs in the piston of your car. In which scenario is your change in internal energy always negative? When the piston moves up or when the piston moves down? So let's walk through this. So the equation for change in internal energy is Q plus W. I actually already gave you the sign of one of them. In the first sentence, I said it's an exothermic combustion reaction. So which term did I give you, kind of? Q, yeah. So what is the sign of Q here? Negative, yay. All right, so my goal here is I want a negative value of internal energy. So what kind of number do I need for work to make that happen? Positive. So if a negative plus a positive number, will it always give you a negative number? Yeah, so always. So if what sign of work do I need for it always to be negative? But, so right here, what's the sign of work need to be? If it's a negative value, yeah. So if work is negative, two negatives, add them together, will you always get a negative value? Yes. But if I have a negative and a positive number, will I always get a negative value? Not always. Sometimes you would, but not always. So we are looking for the example where we always get a negative value of internal energy. All right, so that is not my answer. All I did was figure out, okay, I am looking for the scenario where work of the system is a negative value. So now we need to further apply that to, is it when the piston goes up or when the piston goes down? Is work negative? Which one do we think it is? When the piston goes up, yes. So there's a couple ways you can do this, all right? We have to think work is negative of our system. So is the system gaining work? Are we squeezing our system? Nope. The system is giving off work to the surroundings. So that means that its volume is changing. How? It's increasing. Yeah, if you just think about it, if you put work onto a balloon, you're going to make it smaller, so volume decreases. So we are looking for the scenario where volume increases, so the answer is when the piston moves up, moves up. Yes, volume moves up. Or you don't even have to think about it conceptually like that. Just plug this into the equation. Work of the system equals negative P delta V. In what scenario will you get a negative work? When delta V is what sign? Positive. Yes, when delta V is positive, when the change of the volume of your piston increases. So when the piston moves up, that means that your work is negative, right? So this one was definitely a little bit more steps, more conceptual than just adding numbers. All right, okay. We're looking confused here. Okay, remember, you are not the system. You are the surroundings. Okay, yes, be when, there we go. All right, so in general, when we look at objects, you know, solid, liquid, gas, we understand that, you know, these different phases, we increase our temperature in order to turn a solid to a liquid to a gas. We also change how those particles are arranged also, so we're changing potential energy. So typically we can, you know, with confidence say that solids typically have lower potential energies, gases have the highest, all right? So the great thing about these energy changes is that if I know the energy change to go from a solid to a liquid, and I know the energy change to go from a liquid to a gas, all right? we can actually also determine what is the energy change to turn a solid into a gas by adding up those steps. So these energy change steps are additive, meaning, or I guess if we're using terminology here, that delta E is a state function, meaning that all we care about is where we start and where we end. And we can take whatever path we want to get from beginning to end. So the thing that's actually measured here, change in internal energy, we're just looking at the beginning and the end, and that is the energy change we're looking at. All right, so that's what I say here, that if we wanted the energy change between these two states, we could add up those subsequent steps. And we'll be doing that, and that's basically the foundation of Hess's law, where we just care about what we start with and what we end with. That also means what the reactants are and what our products are, right? Okay, so the thing is, we've been talking about internal energy here, delta E, but from here on out, since we are doing just benchtop chemistry, typically at constant pressure, 1 atmosphere of pressure, we can actually instead talk about energy changes in terms of enthalpy instead. So this delta H term, very, very much closely related to delta E, but because everything is involved with heat, and since everything is at a constant pressure, we're just going to ignore the work aspect that's being conducted for these reactions. So we're just going to be looking at that heat component, which we call delta H. Still think of it as energy, but we're just worried about the heat component here. All right, so we'll be looking at heat. Enthalpy here is also a state function, so we just care about the beginning and the end. And when we talk about like positive delta H's and negative delta H's, all right, our endo and exothermic terms still exist. So we're just going to be focusing on heat now, where we're looking at the delta H component, enthalpy component, instead of the total internal energy part. So we're not going to be looking at work so much. All right, so, okay, enthalpies, delta H, energy, heat. All right, so I'll introduce to you a new kind of equation. All right, we did balancing equations in chapter 3, but now we're adding this energy component into it. So we can actually add that delta H component to a balanced chemical reaction. So this is called a thermochemical reaction, where we add this delta H component, all right? Oh, that's not the slide I wanted to actually talk about. So I thought this was a different slide. So what you see right here is a thermochemical equation. We've done this equation, right? We've done this reaction. We've made water. We've turned hydrogen gas, it reacted with oxygen gas to make water. So this delta H that is tacked on the end is just telling you that this reaction, if 2 moles of hydrogen react with 1 mole of oxygen, you will release 484 kilojoules of energy. All right, so this is a full thermochemical equation where we have the energy component in there. All right, so I mentioned that enthalpy is an extensive property, meaning that depending on how much stuff you react will change how much heat is produced. That kind of makes sense, right? If you have a full tank of gas and you can go like 400 miles on a full tank of gas, right? That amount of fuel gives you this amount of, energy output. But if you only have half a tank of gas, how far can you go? Yeah, half of the distance, so 200 miles, right? So enthalpy works the same way as well. If we have a reaction, is that what I do here? Yeah. All right, so this reaction releases 484 kilojoules of heat, but if I have the reaction, how much heat is actually given off for this halved one? Yeah, so half, so it's going to be like negative 242. Yeah, so I have the reaction, I have the amount of heat that comes out. All right, so if I doubled the reaction, I would double the amount of heat would come out, right? Okay, so I double enthalpy. So if I reverse a reaction, all right, so if you look really closely here I'm taking hydrogen gas and oxygen gas making 2 waters. But in this reaction, what am I doing? I'm doing the opposite. I'm taking 2 waters and I'm decomposing it, I'm splitting it back into hydrogen and oxygen. So in this example, I didn't double it or triple it. What did I do? I flipped it. Yeah, I flipped it. So if you flip a reaction, if you do the reverse of a reaction, what you do is actually change the sign of enthalpy, of the energy change. So instead, for this reaction that's flipped, this reaction actually requires 484 kilojoules of energy. When I do the combustion reaction, it releases 400 kilojoules of energy, but if I want to split water, if I want to do the opposite, if I want to undo it, I actually have to give the reaction 400 kilojoules of energy to do it in reverse, right? Okay, so this is the basics of Hess's law. Whatever you do to a thermochemical equation, you have to also do to delta H, right? If you have a reaction, you have to have delta H. All right, states are important too. That will change your delta H as well. Like for example here, if we make H2O liquid versus a gas, the energy output is a little bit different. The energy value that's written there. All right, okay, this is the slide I thought I was talking about. Okay, so let's balance a thermochemical equation. All right, so I'm telling you that the combustion of methane, CH4, with oxygen is exothermic, and it produces that much heat per mole of methane. Let's write the balanced chemical equation. So this is our combustion of methane, so we can probably fairly easily balance the carbon, hydrogen, oxygen part. So looking here, for every mole of methane, I need 1 mole of CO2. How many moles of water do I need? 2, okay. And then how many O2s do I need? 2. There we go, 2, yeah. All right, so that's balanced. To make it a thermochemical equation, I need to add this energy component, the delta H. But we need to be careful. Is it just 890? No, it's actually what? Negative 890 kilojoules. There's a couple hints here. I tell you it's exothermic. Okay, I tell you it's exothermic, so it should be a negative sign. Also, I say that it's 890 kilojoules of heat released. All right, the reaction releases it, so it's a negative sign. All right, so the sign here tells you whether energy is, heat is being released or absorbed by your system. All right, that's what the sign tells you. Okay, so what's great about this, what was the special thing with the coefficients here? We could use them in stoichiometry if we were in the unit of moles. So these coefficients are really nice because if we're in moles, we can go wherever we want based on the stoichiometry. Now with this delta H term, we can actually say the same thing. So I can say for every 1 mole of methane, I need 2 moles of O2. Right? But I can also say, so I could go to methane, I could go to O2, but I could also go to delta H as well. So for every 1 mole of methane that reacts, 2 moles of oxygen reacts, but what also happens is that 890 kilojoules of heat is released for every 1 mole of methane that reacts. So with this new delta H term, we can actually include it in our stoichiometry that we've said before. All right, so it's this new term that we can use as long as we're in the unit of moles. So let's look at this question that says, okay, how much heat would be produced if we consume 24 grams of methane? All right, in excess oxygen. So the stoichiometry I want to use here is the relationship between methane and delta H. So for every 1 mole of methane, CH4, 890 kilojoules of heat is released. I mean, I can put the negative sign there as well to mean released, but I actually like to say released, okay? The negative sign also implies the same thing, okay? So this is just stoichiometry, all right? I'm just giving you a new tool in your toolbox to use in dimensional analysis. So you know how to do this, convert methane into moles. We start with 24, that was given. So molar mass of methane is 16 grams, is 1 mole of methane. Now I'm in moles, so I have the ticket to get on the bus. That is the chemical equation. This time it's thermochemical, so we can go anywhere we want. So we look at the coefficients. For every 1 mole of methane, we can go anywhere we want. If we wanted to go to oxygen, we could put 2 moles of oxygen on the top, but we don't want to go to oxygen. We want to go to heat. So instead, we're going to put 890 kilojoules up top, and that's heat released here, released. All right, and then you multiply that together, how much heat's released? 1330 kilojoules. All right, or you could put the negative sign. I guess that's what my key has here. And then that negative sign implies that the heat is released in this case, released, that negative sign. All right, okay, that's exothermic. We know this because this is a combustion reaction. All right, so let's do another one. Let's say that 2,400 kilojoules of heat is produced, so is released by this reaction. How many grams of water is also produced? All right, so in this example, I'm giving you how much heat is produced, but I want you to go to water. And we can do that just using stoichiometry. But this time we want to use the relationship that says for every 2 moles of water, 890 kilojoules of heat is released in this case. All right, so see how it's just stoichiometry, but with this delta H step, right, where we keep those coefficients. All right, so it's 2 moles of water gives you 890 kilojoules of heat. Right. All right, so we start with 290 kilojoules. All right. Again, I don't want you guys to get confused with this negative sign because here I'm telling you heat is being produced, it's being released by this reaction. So that negative sign isn't super necessary here. We can still use the relationship 890 kilojoules of heat is released. We also get 2 moles of water in that process based upon the stoichiometry up there. All right, so released, I guess I can put released for both of them. Okay, the sign just tells us the direction. And then this question asks for grams. Right now we're in the unit of moles, so you know how to do that. For every 1 mole of water, it's 18 grams. All right, and then you get your answer over there. If you make that much energy, you will also make 97 grams of water in the process. All right, so just stoichiometry. Okay, so we're adding this delta H component to our toolbox. It's no different than chapter 3. As long as you're in the unit of moles, you can go wherever you want on your bus route, including delta H. Okay, all right, so there's reaction stoichiometry. Okay, that's how your car knows how far you can go. You're on like half a tank and somehow your car knows like, oh, you only have like 200 miles left. Estimated, yeah, that's basically what it's doing, right? Okay, so how else can we talk about delta H? And that is using Hess's law. I mentioned before that these energy changes are state functions, so what we only care about is where we start and where we end, our reactants and our products. So what we can actually do is add together reactions in such a way to get this target reaction, all right? I don't have to go from reactants to products in one step. I can start with my reactants, make some stuff that's like an intermediate, take those intermediates, make some more intermediates, and then finally go to my products. So what delta H measures is just, okay, what's the net distance or net energy change you made? So we can add up different steps to reactions to give us an overall energy change for that final minus initial step. So there's a strategy to Hess's law. It's like a puzzle, right? We want to add up different reactions in such a way to give us a target reaction. But we just need to make sure we apply those rules of extensive properties. If we double a reaction in order to get it to match, we also have to double delta H. If we reverse a reaction, we have to change the sign of delta H before we add everything up. All right, so those are the things here. So we want to check direction of our reaction. If it doesn't match, then we flip it, but do that to delta H as well. Check the quantities or coefficients, multiply by the appropriate numbers, but also do that for delta H. So when we add up these reactions, oftentimes we'll cancel out what look like intermediates. So if we add up these reactions and, for example, if substance A shows up on both sides, A will just cancel out of our reaction and hopefully give us our target reaction. Or in this example, we have two X's and an X on the product side, so only one X cancels. So you're left with one X on the reactant side. All right, so it's just like a little puzzle. Okay, so I think it's better if we just do an example. Okay, I have two reactions. Those are our puzzle pieces. And what's the enthalpy change for this reaction? I like to call this my target reaction. This is my target. Okay. So I need to figure out how do I add up these two reactions to get this target reaction. So this is my strategy. Focus on one substance at a time. Focus on one substance at a time. So I'm going to look at this guy and ask myself, which reaction has that substance in it? AB2. Reaction 1, yes. But is it in the right place? Is it on the right side? No. So I need to do what to this reaction? Flip it, yeah. So let's flip this reaction. So if I flip the reaction, what do I have to do to delta H? Times -1. But, so I flipped it. What then, is it in the right quantity? No. So what do I need to do? I need to multiply by 2. So flip and multiply by 2. So I'm going to do both of those things. All right? So I'm going to rewrite reaction 1 that's flipped and multiplied by 2. I'm going to rewrite it so we can see how things add up. So I'm going to rewrite it. So reaction 1 that's flipped and multiplied by 2, we get 2 AB2s, and then we get 2 A's and 4 B's. And then we'll have a new delta H that is that number. All right, so the delta H for this value is, what is that? Positive 70? Positive 70? Okay, because I flipped it and multiplied it by 2. Okay, so I just used reaction 1. So now we need to figure out how we use reaction 2 here. So let's focus on a different substance. I already got AB2 in the right place. So let's look at another weird thing. I'm going to not try to get B in the right place, because if you notice, B is in both reactions. So what I'm going to do is just ignore it and pray that it cancels out to the number I want. So I'm going to actually focus on this weird guy, A2B5, because it only shows up in one reaction. All right? So we ask ourselves, is A2B5 in the right place? Is it in the right quantity? Yeah, so do I need to do anything to it? Nope, so I just rewrite it exactly as is. So I'll do that. So reaction 2, we're going to do nothing to it. It's 2A plus 5B gives us A2B5. Its delta H does not change at all. Okay, but I'm still adding it to the other one. So let's see, how do these reactions, when we add them up, how do they cancel? What cancels here? I'm going to try to make it look nice. So we're adding these two reactions up. So it looks like the A's cancel, right? Because they're on opposite sides of the arrow. Those cancel. And then how many of the B's cancel? 4 of them, yeah. So 4 of the B's cancel, and then how many are we left with on the reactant side? Just 1, yep. And so when we add up those reactions, we see we are left with 2AB2 plus a B gives us A2B5. So check and see, is that my target reaction I wanted? Yes, it is. And so then we can go ahead and add up those delta H's, and you do get, in fact, this is negative 20 kilojoules. Okay? So it's like a little puzzle. So flip, multiply as needed to make those given reactions match your target reaction. Okay, let's do one more that's a little harder. Here is one with 3 reactions. So again, I like to just take it one substance at a time. All right, I'm going to look for a reaction that has carbon in it. Okay, focus on one substance at a time. This is my target reaction. Okay, so which reaction has carbon in it? Reaction 2. So then I ask myself, is carbon in the right place? Yes, but is it in the right number? No. What am I going to do? I need to double it. So that means I also need to double delta H. All right, so I'll just do that. So this is reaction 2 that's doubled. So 2 carbons, I'm going to drop the states. 2 oxygens give us 2 CO2s, and then the new delta H is negative 394 times 2. That's the new delta H. Okay. All right. Next, let's look at C2H2. Okay, which reaction has that guy in it? Reaction 1. So for reaction 1, is it in the right place? No, so we gotta flip it. Flip it. Is it in the right number though? Yeah, so we just have to flip it. So we just have to multiply that delta H by -1. So this is reaction 1. That is flipped. So 2 CO2s plus a water gives us C2H2 plus 5/2 oxygen. Since I flipped it, delta H changes to now positive 1300. All right. So now we have to look at reaction 3. Well, I guess, yeah, let's look at the last substance here, H2. Okay, let's pick a different highlighter color. H2, which reaction has H2? It's the last one that we didn't touch yet, and that's reaction 3. So we ask ourselves the same thing. Is it on the right side? Yes. Is it in the right number? Yes. So we don't actually have to do anything in terms of manipulating it. We just add reaction 3 as is. So I'll just write that as is. So this is reaction 3. Reaction 3, I'm just going to rewrite it. So H2 plus half an O2 gives us a water. And so I rewrite this value as is, so minus 286. Okay, so those are the 3 reactions that I've manipulated. Let's check to see if we get our target reaction. So if you look at these arrows, when you add these things up, all of these will be reactants. All of these are going to be products. So I can just note and see, oh, CO2 is a product over here and it's a reactant over here, so it cancels out. So CO2 cancels out when I add those 2 reactions up. What else cancels? H2O, yay. Yay, and then what else cancels? Some of the oxygens? Or all of the oxygens, right? Yeah, so 5/2 is equal to what? 2.5. And then this is 2 oxygens and half an oxygen. So there's a total of 2.5 oxygens here. Yep. So all of the oxygens cancel out too. Yep. And so are we left with our target reaction? Yes, we are. Okay, then good. We checked our work. We can go ahead and just add up all of those enthalpies with those appropriate manipulations. And so when you add all of those up, you get, hopefully, positive 226 kilojoules. Right? So we are highlighting, Hess's law is highlighting the idea that enthalpy is a state function. All we care about is where we start and where we end. That energy change, we can take as all the different steps that we want to get there, all right? Make all these intermediates, that energy change, overall net energy change will still be the same, right? Heat and work are not state functions, okay? But if you take an engineering or thermodynamics class, you'll learn more about that. But we're just utilizing the state functionness of enthalpy for this example. Okay. So that's Hess's law. That's one of the first ways that we will calculate enthalpy using Hess's law. That is a learning objective. Can you do the puzzle? Puzzles are fun. If you look at my overview sheet, there's an example I have with 6 different steps in it. And you can try it out. Try it out. Okay. All right, so let's move on to the next way to calculate enthalpy, and this one's much harder. This one is going to help you for that IHT lab. Okay. I also, if you look at chapter 5, our page, I have a nice graphical explanation of calorimetry. All right. There's a document there. It's a colorful document of how to do IHT. Okay, so you can read that on our page. All right, so calorimetry. This is how we experimentally determine enthalpy of a reaction. All right, so in Hess's law, what we just did, we used known reactions to like piece together a new reaction. It's all theoretical, it's all book numbers. So calorimetry is how do I go in lab and calculate what delta H is of something, all right? And so we need to get some definitions out of the way, and that is heat capacity and specific heat. So these are ways that we can measure heat involved in a process. We just need to make sure we get them right. So heat capacity is the amount of heat it requires to raise an object 1 degree Celsius, okay? An object. So it depends. So the heat capacity of an object, it depends on what kind of object it is. If it's a small object, then it probably doesn't need that much heat to raise it. But if it's a huge object, it's going to take a lot of heat to raise the temperature of that whole object. All right, so heat capacity is actually an extensive property. The unit for it is joule per degree Celsius or joule Kelvin. All right, so if you note the equation here, C over Q, so heat involved in the process, over the change of temperature that it underwent. In this chapter, we're going to be talking a lot about delta T's, changes in temperature. So what we'll see is delta T when it's like 10 degrees Celsius or 10 Kelvin, those are actually the same thing because it's a delta T. 10 degrees Celsius and 10 Kelvin, they're not the same temperature, but when it's delta T, it's the same thing. I'll prove it to you. So if something goes from 10 degrees to 20 degrees Celsius, what's delta T? 10, yes, okay, good. Okay, great, so 20 minus 10. Okay, what is 10 degrees Celsius in Kelvin? 283 Kelvin. What's 20 degrees in Kelvin? 293 Kelvin. All right, so take the delta T of those two Kelvin temperatures. 10, it's 10 Kelvin, all right? So that's proof that this joule per degree Celsius or joule Kelvin, it's the same thing when it's a delta T, all right? Regardless if you're in Kelvin or degree Celsius, as long as it's a delta T, the difference increment is the same. All right, so that's heat capacity. On the other hand, specific heat is specific to the identity of that object. It's kind of like density. So this is the amount of heat required to raise a gram of that object's temperature by 1 Kelvin or 1 degree Celsius, because it's the same thing. I guess I should say that. Or 1 degree Celsius, or 1 degree Celsius. All right, and so this idea, specific heat, is like, I'll give you the specific heat of gold, right? Gold has a specific heat where, you know, gold, 1 gram of gold anywhere will always require this amount of heat to heat it up. All right, so what we see here in the unit is that there's this mass variable now, and now we have this mass unit on the bottom of our denominator. All right, and so these are 2 different equations that we will use in calculating heat involved in a substance. We just got to be really careful when we use what, because don't these equations kind of look the same? Yeah, they kind of look the same, don't they? So we need to be really careful. Are we talking about heat capacity for a whole object, or are we talking about specific heat in the identity of an object? All right, and so the idea here also is delta T is always final minus initial, always, always. Any delta, like delta V, it's always final minus initial. So keep that in mind so we get our signs straight. Okay, here are some examples of specific heats. So you can see that this is the joule per gram Kelvin unit. All right, so all of these values are how much heat it requires to raise a gram of any one of these substances by 1 degree Celsius. All right, so what do these numbers mean? We have a lot of numbers. We have numbers that are like half a joule gram Kelvin, or water has a fairly high specific heat, 4 joules per gram Kelvin. And so the differences in these numbers, if we think about the unit, it's joule per gram degree Celsius. How many joules do you need to raise a gram 1 degree Celsius? So if we have a large specific heat, all right, a large specific heat means you need a lot of heat to increase the temperature of 1 gram of substance, right? You need a lot of heat. That's what a large specific heat means. A large specific heat also means that that substance, its temperature is not easily changed, right? That we'll see less variability in that temperature. If you think about like the lake effect, or maybe, you know, like how temperate like coastal areas are. Coastal areas are surrounded by water. Water on our table has a very, very high specific heat, meaning that it's these heat sinks. That, you know, sunlight energy comes down, heats up the water slowly, absorbs all that heat instead of heating up the area around it. So those coastal cities tend to be more temperate in temperatures, not huge fluctuations like there is in Ohio. Okay, so I promise you, you subconsciously understand specific heat. Okay, so pretend it's a really, really hot day. You just went on like a 10-mile hike, and you see two benches. Okay, you see two benches, and they're out in the sun, and you have the choice to sit on a metal bench or a wooden bench. Which one do you sit on? The wood. Why do you sit on the wooden one? Because it's probably cooler, right? It's probably cooler. So you tell me which object, aluminum or wood, has the higher specific heat. Which one has the higher specific heat? You told me you want to sit on the wood one because it's probably going to be cooler, right? So which one has the larger specific heat? Wood, yes, wood has the larger specific heat, larger because that substance, the temperature is not easily changed. So metal here, aluminum, has a specific heat of about 0.9. I think wood has a specific heat of something like 2.6 joule per gram degrees Celsius. So almost double, more than double. Yeah, okay. So you know. All right, so let's do some calculations. All right, okay. And make sure, which equation do we use? Do we use the one with specific heat, or do we use the one with heat capacity? Let the unit tell you. Okay. How much water in kilojoules is required to heat up 100 grams of water by 75 degrees Celsius? That's its specific heat. So what equation do we use? The first one or the second one? The first one, yeah, because I give you specific heat, right? And I give you mass. So we want to use the one with mass in it. So at this point, it's just like kind of plug and chug. So Q equals mass, so 150 grams. Specific heat, I give it to you, it's 4.184 joule gram degree Celsius. And then delta T. So I just told you, heat up the water by 75 degrees Celsius. So I could have started anywhere, but I'm actually telling you straight up that this is delta T. Delta T is 75 degrees Celsius. Right, I could have given you a final and initial temperature, but I didn't. All right, so 75 goes there. All right, so we just cancel stuff out. You see the grams cancel, Celsius cancels, and you do see, in fact, we are left with the value of joules. Right, and so you calculate this, you get something like 53,000 joules or 53 kilojoules of heat is required to heat up all that water, right? That's just like a small cup of water, right? Okay, that's like boiling a little cup of tea in the microwave. That's how much energy you need to heat it up, okay? Water is a huge heat sink. All right, so let's look at this next one. If 250 kilojoules of energy is delivered to a 6-pound cast iron pan, and it has a total heat capacity of that, how many degrees does the cast iron pan increase? Which equation do we use? The first one or the second one? The second one. Why the second one? The heat capacity. Yeah, I said total heat capacity. Also, look at the unit of that heat capacity I gave you. Is there a gram value in it? No, there's not. So we actually want to use the second equation. But I gave you 6 pounds. Where do I use that? You don't need to, because it's that 6 pounds. The weight of it, the mass of it is already tied up in that total heat capacity. It's already accounted for. Right? So we're going to use that second one, but we're solving for delta T this time. So Q in this case is 150, but I'm going to convert that to joules. Oh, no, I'm not, because the heat capacity is in kilojoules. I don't have to. Okay, equals heat capacity, 1.2 kilojoule degree Celsius times delta T. So I'm just solving for delta T here, and you get 208 Celsius, right? So delivering that much heat given this heat capacity will raise the temperature of that pan by like 200 degrees Celsius, right? And so I tried to trick you by telling you the weight of the pan, but I didn't give you specific heat. I gave you total heat capacity, so you don't have to use it at all. All right. Okay, so let's do some more conceptual things. Let's compare without doing any calculations. Which object, so a cup of water or a pool of water, which object has the larger heat capacity? A cup of water or a pool of water? The pool of water, yeah. So really what I'm asking you here in this question is which object requires more Q, more heat to raise it 1 degree Celsius? Which object? Is it the whole pool or the cup of water? So in this case, the whole pool, it's going to take a lot more energy to raise it a degree. But then which has the larger specific heat? They are the same because they're both made of water. All right, because the idea here, specific heat is joule per gram degree Celsius. If we're just comparing a gram of each of them, they're both going to have the same specific heat. But where these two objects differ is their size. The pool has much more mass involved there. So that's how we see specific heat and heat capacity are related. There's that mass component involved in heat capacity. All right, that's what I have here. Heat capacity for an object is equal to its specific heat times its mass. That's how we get rid of the gram unit on the bottom. All right, so heat capacity is C. Is it extensive or intensive? Extensive. And then CS, specific heat, is intensive. Yep. Great. Okay. Cool, we have 15 minutes. All right, let's go on to the hardest part of the chapter. Okay, two types. The ways we actually, we got all the definitions out of the way, so let's actually put it into the context of a chemical experiment, and that is calorimetry. There's two ways we will study calorimetry. One is coffee cup, and the other one is bomb. You will do coffee cup in lab and in lecture, but we'll just do bomb calorimetry in class, but you won't do it in lab. And bomb calorimetry is a lot easier to calculate, in my opinion. Okay. So we do bomb calorimetry when gases are involved, but when reactions are really simple, like acid-base reactions or dissolution reactions, coffee cup is fine because no gases are involved. All right. Okay. There's a lot here. Okay. This is what you need to know for coffee cup calorimetry, which you will do in IHT. You are the surroundings. The reaction is the system. So when you put your thermometer in the cup, all right, you're going to fill that cup with water. You're going to do a little reaction, and you're going to stick your thermometer in it. We need to be really sure, what is that thermometer measuring? Yeah, it's going to measure like a temperature change, right? But the temperature that it's measuring is of the water. The water is the surroundings, okay? So this is the chemical. Did I write the chemical reaction here? No, I didn't. Okay, so here. This is the system, this chemical reaction. HCl particles reacting with sodium hydroxide particles. All right, that's an acid-base reaction. But when we think about what's happening in the cup, it's happening in a sea of water molecules. So that water, like all the rest of the water in the cup, that's actually the surroundings that we are measuring. So any heat that is given off by the reaction is going to enter the water that we're measuring as the surroundings. All right, so with that in mind, and the first law of thermodynamics that says any heat that is lost is gained somewhere else. If the system loses heat, it's gained by the surroundings. So we can also say if the reaction gives off heat, it's gained by the surrounding solution, the water. All right, and then we will use these Q equals MCAT or Q equals heat capacity delta T calculations for these different Qs. So the idea is the reaction will either release or absorb heat. We are monitoring that by monitoring the temperature of the surroundings. So if you do a reaction and in your thermometer, okay, you mix some stuff, you put your thermometer in, and you see the temperature increase, what kind of reaction is that? What kind of reaction is it? What kind of reaction was the hydrogen balloon? Exothermic, right? So what's the sign of delta H? Negative. Yes, it's negative. Which is weird because you saw the thermometer temperature shoot up, right? But no, the reaction gave off heat. What we are measuring are the surroundings. Or conversely, okay, if you do a reaction and the temperature of your thermometer goes down, it means that the surroundings is losing heat, right? So that means your reaction is gaining heat. So what is the sign of delta H in that instance where the temperature of the thermometer goes down? Positive. It's an endothermic reaction, all right? This is super important. Intuition, using your intuition to just get the sign right, all right? So we have 10 minutes, so we will do that question right here. This is a common exam question. And once we finish it, I'll tell you guys a story. Okay, so we have 6 grams of sodium hydroxide and it dissolves in 100 grams of water. The entire solution changes by that much. The specific heat of the solution is the same as water. Calculate the enthalpy of this reaction. Okay, so the idea here, this is the reaction. We're taking sodium hydroxide, solid, we're mixing it with water to make sodium hydroxide aqueous. We are trying to calculate delta H. So these are the steps. The first thing you should always do is use your intuition to just figure out what the sign of delta H is. So based upon the information given, does the temperature of the thermometer go up or down? It goes up. So what should the sign of delta H be? Negative, yes. Okay, so make sure before you put an answer down on the exam that it's a negative sign. Because you know for a fact if we give you options, we will give you both a negative one and a positive one. All right? Okay. All right, so the next strategy is we need to figure out, based upon our observations, how much temperature the water raised, how much Q was involved in this reaction. All right, so these are these useful equations. Recognize that heat lost somewhere is gained somewhere else. So we're going to say the heat that is gained by the solution is lost by the reaction. So negative Q reaction equals positive Q solution. All right, we can't measure the reaction directly, but we can measure the solution because that is where our thermometer is. Our thermometer is sitting in the entire cup, but the thermometer is not touching the individual particles. We can measure the solution, we can't measure the actual reaction. So let's think about what is the Q equals MCAT stuff for the solution. All right, so we are actually going to use, okay, so negative Q reaction equals, we're going to Q equals MCAT this, so Q equals mass of my solution times the specific heat of my solution times delta T of my solution. So we're going to ask ourselves, how heavy is the solution? What's the specific heat of the solution? How much temperature did the solution change? Okay, some of these we can get fairly easily. Our temperature change was given. It's right there. That's delta T of the solution. Right there. All right, so delta T, remember, delta T is always final minus initial. So this is going to be a positive number. So it's 37.8 minus 21.6. So this is, I wrote it down. What is it? Dang it. 16.2. Okay, degrees Celsius. That's delta T. Got it. What is the specific heat of the solution? 4 point whatever. They gave it to us. It's the same as water, so it's 4.184. What is the mass of the solution? Be very careful here. What's the mass? Think about what is in your cup. Everything in your cup. 100 grams of water and 6.5 grams of the salt. So the mass of your solution, all right, is the mass of your water plus the mass of the solid here. All right, so the mass of your solution is actually 106.5 grams, not 100 grams. Okay, if you think about what's in your cup, we have 100 grams of water and 6.5 grams of salt. So the mass of the solution is both of them. Okay, so we have all of those values, so it's just plug and chug now. So mass of your solution is 106.5 grams. Specific heat is 4.184 joule gram degrees Celsius. Delta T is 16.2. All right, multiply all those things together and you see that 7,220 joules of heat was involved to heat up all of that water. Right, that's how much heat was required to heat up that water. Okay, so if the water heated up, the reaction was what kind of reaction? Exothermic. That's why we need that negative sign. See how I didn't apply that negative sign yet? So the Q involved in this reaction is actually negative 7,220 joules. All right? Because it's an exothermic reaction. That's why you need that negative sign. Okay. This is not my answer. I want not Q of this reaction, I want the enthalpy of the dissolution of sodium hydroxide in the unit of kilojoules per mole. So I need to scale this to a mole amount, because right now this heat amount is just how much heat was produced when I dissolved 6.5 grams. I want to scale it to a mole amount. So how I'm going to do that is recognize that delta H for a reaction is equal to the Q of that reaction over the number of moles that I actually dissolved in that reaction. So that's how I get it into a mole amount here. All right, so I'm using this equation right here. So I'm going to take that value I just calculated, Q of my reaction, with the appropriate negative sign. All right, so I'm going to convert it into kilojoules. So negative 7.22 kilojoules of heat divided by the number of moles I actually dissolved. So in this case, I only dissolved 6.5 grams of salts, and so I need to convert that to moles. What is the molar mass? 40. 40 grams is 1 mole. And that's how I get a enthalpy of dissolution for this process is negative 44 kilojoules per mole. So I did all of the Q equals MCAT stuff and got a Q amount for this specific reaction. And then to get it to delta H, I need to scale it to a mole amount by dividing by how many moles I actually reacted. All right? Okay, so this is one of the hardest kind of problems in chapter 5. And so this is an example of a question that I would say you should skip on the exam and just save for later if you have time. And so the story I was going to tell is the first year I taught here, whenever I got the midterm, right, the copy of the midterm to check, I would do the exam under exam-like conditions. And I would try to do it as fast as possible, just for fun, to see if I still had it. And so this exam, midterm 2, my first year here, I did in 7 minutes. I did it in 7 minutes, and not to brag, all right, I did in 7 minutes, but I got one question wrong, and guess which question it was? It was this one. And it wasn't because I missed the mass. I know to add the mass of the water and the salt. I know to do that, all right? Why did I get this question wrong? I messed up the sign. Yeah, so I did not report negative 44. I reported positive 44. I did all the math right. I just got the sign wrong. Yes. Okay, so have a good weekend. Remember, chapter 4 homework is due. Yes.